All right, so let's just go ahead and get it started. Today, we're very happy to host our CRML Distinguished Lecture Series. And today we'll have Professor Cynthia Rudin from Duke University. And Professor Cynthia Rudin is Professor of Computer Science, Electrical and Computer Engineering, Statistical Science, Mathematics, and Biostatistics and Bioinformatics at Duke University. She directs the Interpretable Machine Learning Lab. Before Duke, Cynthia was at MIT, Columbia, and YU. She has a very distinguished career. Her PhD is from Princeton University, and she's a recipient of the AAAI Squirrel AI Award for the benefit of humanity. So this is, for those of you who don't know, this is a amazing award that the AAAI created in the last, it just started, I think, 2 years ago, to really honor the best and the brightest in the field of artificial intelligence that rivals the Nobel Prize and also the Turing Award from ACM. So Cynthia is also a fellow of the AAAI, and she has also been recognized by so many other awards. For example, the 2022 Guggenheim Fellow, and she's a fellow of the American Statistical Association, the Institute of Mathematical Statistics. So without further ado, let's turn it to Cynthia, and she will tell us her work in the area of interpretable machine learning. So welcome, Cynthia.
Thank you. I'm going to just share my screen here. So hopefully you can see that. And I'm going to talk about the extreme of interpretability in machine learning. Back in 2015, we wrote an article called Interpretable Classification Models for Recidivism Prediction. And in this article, we used the largest public data set on criminal recidivism. It was like over 33,000 people who were all released from prison all in the same year. And we used interpretable machine learning tools to predict whether someone would commit one of a bunch of different types of crime, like after they were released from prison. So we were trying to predict like misdemeanors, violent crimes, sexual crimes, property crimes, drug crimes, you name it. And what we showed was that we don't need a complicated model to predict criminal recidivism. And race was not a useful factor in predicting recidivism. Now, we were pretty surprised when the ProPublica article came out a year later, claiming that there's a proprietary model that's used throughout the US justice system. It's called COMPAS, and it depends on race. And we were like, wait, hold on, what's going on here? Like, first of all, no one in their right mind would design a model that uses race. Race is correlated with other stuff you might want to use, like criminal history and age, but those correlations are due to systemic racism in society. That doesn't mean the model incorporates race. Our paper says that if you take into account age and criminal history, you don't need race, right? There's no predictive power coming from race. So we were like, okay, so we were thinking about it and we were like, okay, what's going on? And then we realized like, okay, why are we having this debate at all, right? The setup for this whole situation seems really bizarre, right? How did we even get into this situation in the first place where we're debating this? We don't need proprietary models for predicting recidivism. We can do it with very simple models that are small enough to fit on an index card. We don't even need to debate about whether the COMPAS model uses race if we can just throw the whole model out and replace it with something that we can understand and troubleshoot. So given that these models determine people's freedom, they really shouldn't be proprietary. And if we were right in our paper, we can actually throw the whole COMPAS model out. So we were wondering, like, how accurate is this proprietary model anyway? Like, is this thing really, really accurate? Because then I could understand why you'd want to use it, right? So we took the data from the ProPublica article where they had COMPAS scores, and we compared it to compared the accuracy of COMPAS to the accuracy of the latest decision tree method in our lab that we developed at the time, which is called Corals. And Corals creates optimal one-sided decision trees. And it's a very complicated algorithm, but it produces really tiny little models. And we ran the compass data through corals, and it created a machine learning model for predicting recidivism. And the whole model is so tiny that it fits in the corner of a PowerPoint slide. And so the model says if the person's age is 19 to 20 years old and they're male, predict arrest within 2 years of their compass score calculation. Else, if they're 21 to 22 years old and they have 2 to 3 prior offenses, then predict arrest within 2 years of their compass score calculation. Else, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we thought, okay, that's really simple. How in the world could this compare to compass, right? Is it as accurate as compass? Does it stand a chance? And surprisingly, it did. In fact, here, this is tenfold cross-validation. So here I'm showing you test set performance for each of the folds, and then the colors are just the different folds. And you can see that even across folds, they performed about equally accurate. And so we thought, okay, we'll just throw the arsenal of machine learning at this problem. And we threw a whole bunch of like black boxes at the problem to see if we could get any more accuracy, and they all performed about the same. And so some of these are like really complicated models, like boosted decision trees and support vector machines with radial basis function kernels. Like all of these are like formulas that you could not fit on a PowerPoint slide. They're so messy in lots of different logical conditions or exponentials and all kinds of other stuff. Whereas for corals, right, the whole model is just right there in the corner of the slide. And so, yeah, so there was this huge debate about like algorithmic fairness of compass, but the truth is that we just don't seem to need compass at all. So anyway, as it turns out, this is not the only data set where simple models perform well. There are actually many data sets where this kind of thing happens, where a simple model performs as well as the best black box machine learning model that we can possibly come up with. And in fact, this happens really often, like surprisingly often. And like these are applications that I've worked on, and for none of them did I require a black box model. And in fact, the truth seems to be that as long as your data have a pretty good representation, then it's essentially universal that interpretable models can perform well, which means that it could be, like in the case of compass, that we are using complicated or proprietary models when we don't need them for high-stakes societal decisions that determine important outcomes for people like their freedom or whether or not they can get a loan. Now, in any case, there's a bit more nuance to what I'm saying here because interpretability is not the same thing as simplicity. So there are really two fundamentally different types of problems that we encounter in machine learning. Problems with tabular data and problems with raw data. So tabular data look a little bit like that, like features, real value and features and categorical features. Whereas raw data looks like images or sound waves or large amounts of text. And these two problems are almost like two different worlds of machine learning. Because for the raw data problems, the only technique that's really working right now is neural networks. And that doesn't mean you can't have interpretability. You just have to think about what an interpretable neural network might mean. And that's a talk that I can give on another day, but not today. But in any case, for tabular data, as long as you're willing to do some minor pre-processing of the data, all the methods tend to have similar performance, and that includes very sparse models like decision trees or scoring systems, which are sparse linear models with integer coefficients. So these are like really tiny little models that you can fit on PowerPoint slides tend to have very good performance. Now, it's really curious why this happens, though, because, it's kind of unintuitive, right? You'd think more complexity would get you better performance. So we've been wondering, like, why are we not getting any benefit from complicated models here? Like, it seems that there should be some kind of benefit to adding extra complexity, but that doesn't really happen with tabular data. Like, as soon as you start adding more complexity, you just overfit. Now, I have a theory as to why this happens, and it's a very simple theory. And my theory is that there are just lots of good models. Okay, so let me explain this a bit more. Okay, so my hypothesis is called the Rashem Unset theory, and I have the link. We actually wrote a whole paper about this very simple theory. The paper, unfortunately, has changed names since I've written this slide. The paper was accepted to the FACT conference just a couple days ago. So the new paper is called On the Existence of Simpler Models. And it talks about this Rashem unset theory. And the theory is just that there are a lot of good models. So if you think about the set of all models, I claim that for a lot of data sets, there are just a lot of good models. And then if you think about, okay, let's think about the set of interpretable models. If that set covers the space of all models, so you think about like, the set of shallow decision trees being a good cover for the set of deeper decision trees, or you think about the set of sparse linear models being a good cover for the set of all linear models. And if that's true, then as long as this set of good models covers a significant chunk of the space, like as long as there are enough good models, then hopefully one of them will be interpretable, right? So that's the idea. It's kind of like the big ocean theory. Like the bigger the ocean, the bigger the higher the chance that you'll find a big fish. So, the larger the set of good models is, the larger the chance that you could find a simple function in there somewhere, right? There's so many good models that hopefully at least one of them is simple. So the implications for this is that, if I'm right, and there are just lots of good models for most tabular data problems, then what it implies is that optimizing for simplicity won't sacrifice accuracy. Now, if I'm right, this has huge implications for a lot of high-stakes decisions that are made using data in our society that deeply affect people's lives. And that includes criminal justice decisions that determine people's freedom, for loan decisions that determine someone's ability to purchase a home, or medical decisions that determine life or death. And I've put up a medical scoring system here that is used in intensive care units that I will talk about shortly. So this theory sort of nicely explains why we were able to find accurate models for these data sets without losing predictive performance. It's because these data sets probably admit many good models. Now, I know a lot of you just won't buy this because it's hard for you to believe what I'm saying if you haven't seen it for yourself, firsthand working on lots of applications. So you might say something like, well, what about benchmark data sets, right? This is the way we typically test algorithms against each other. Okay, fine. You want to talk about benchmark data sets? Let's talk about benchmark data sets. So here's a great one. This is from the Explainable Machine Learning Challenge. Now, FICO gave us this data set, and they said, make a black box and explain it. Of course, we didn't do that. We created a model that was inherently interpretable. So anyway, this is a data set about loan decisions, home equity line of credit. So you have all this credit history about everyone, and then you're trying to predict whether they default on their loan. Okay, so we had about 10,000 loan applicants, like a whole bunch of factors about their credit history. And then we ran a whole bunch of black box models on the data set. And the best that we got was, best accuracy we got was about 73%. And the best black box area under the curve is about 0.8. So this is what we want to maintain when we're designing interpretable models. The question is, can we get to those scores and keep the model interpretable? Now, unfortunately for this competition, we had no access to domain experts, which makes it really hard to sort of figure out what they want, what's interpretable to them. So we went to the FICO website, and it was covered in neural networks. And so we thought, okay, maybe we want our model to look like a neural network. But the truth is that what we put together for them was just a whole bunch of sparse logistic regression models just sort of stuck together. And we strung them together to look like a neural network. Okay, so I'll show you that model here, right here. By the way, this model didn't lose any accuracy or AUC over the best black boxes. So we didn't sacrifice any performance at all compared to the black box. But anyway, there are 10 of these subscales. So here are the features right here, the 20 some features. And here are these 10 subscales, each using between 1 to 4 features. And then we combine them into a logistic regression model that used these 10 subscales as inputs. Okay, so there were 11 little itty bitty logistic regression models between these were between 1 and 4 features, and then this one was like 10 features. Okay. So I'm going to just show you what these subscales look like. I'm going to zoom into the subscale in the middle here, which was the delinquency subscale. And the features used in that were like, percent of trades never delinquent and months since most recent delinquency. Okay, so what you're going to see is a tiny little, it's actually a generalized additive model, right? That's all it is. So here, this person who we're scoring right now, their percent of trades never delinquent was between 59 to 84. So they had a bunch of delinquencies. So we gave them some points. They lost some points for that. And then their months since most recent delinquency, well, they were delinquent in the last 8 months. So they lose some points for that. And then we add up all the points. And then we add it to, that's this number. And then we add it to a bias term. And then that gets sent through this logistic function to give you an associated risk. So this person who we're scoring had like almost an 80% risk of defaulting on their loan just based on their delinquency information. Okay, so we had all of these subscales and again, just combined them together in a final logistic regression model. And that's what we did. We just, just some sparse additive models just strung together. And I say sparse additive, by the way, because these are like all these step functions in it, right? It's not just linear, it's just step functions here. And so it's a generalized additive model. All right, cool. So our entry won this FICO recognition prize. And so we were very proud of having gotten to that level of accuracy without actually having used a black box. So what we found was that even on challenging benchmark data sets, the interpretable model's accuracy was equal to the black box accuracy. Now, the judges didn't think anyone could do this, which is why they told everyone to create a black box and explain it. So then let's assume, for the sake of continuing this talk, that you believe me, that there are just a lot of good models, some of which are interpretable. Then the question becomes like, how extreme can we go? Right? How sparse of a model can we actually get and maintain accuracy? Right? Obviously, we know sparsity is not the only factor in interpretability, but I kind of want to know, like, how small of a model can I get? So I'm going to talk about 2 of the fundamental topics in interpretable machine learning today, both of which I've been working on for over a decade in some shape or form. And the first is sparse generalized additive models, like the 2 helps 2B score here. And tell you about that in a minute. And then sparse decision trees is the other one. And these are kind of opposites from each other because additive models are nonlinear. They're nonlinear because like you have step functions like this one, but there are no interaction terms at all. Like you just add stuff up and then that translates into a risk here from this table. So there's no interaction terms, whereas decision trees are like all interaction terms. Okay, so let's start with sparse generalized additive models, and I'm going to tell you about the model on the screen here. So let's say that you have an aneurysm that bursts in your brain, and you have a hemorrhage in your brain hemorrhage. So you have like a blood explosion in your brain. Then you'd be sent to the hospital to get emergency surgery. That would land you, then they would send you to the intensive care unit, where they'd put EEG monitors all over your head to detect for the possibility that you might have seizure or you have seizure-like activity. And seizures are very common in critically ill patients. About 20% of patients get them. Seizures lead to brain damage, they lead to death, and doctors will do like a lot to try to prevent you from having a seizure and having your brain destroy itself. And so they might even like give you drugs to shut off part of your brain for a little while so you don't get a seizure. And the only way to detect seizures or seizure-like activity is through EEG because these are not like seizures where people are shaking. This is all subclinical. It's all in your brain. So if this was you, there's a reasonable chance that you would be scored. Doctors would score your risk for seizure using the 2 helps 2B score that we designed, which is so small that it fits in the corner of a PowerPoint slide. And the name of the model comes from 2 HELPS and then 2 points for the B. So the doctors could memorize the model just by knowing its name. And unlike other medical scoring models, this one wasn't designed by fiddling with logistic regression coefficients. It was actually designed by an algorithm for interpretable machine learning. where the selection of which variables to go in here and these coefficients, all of the stuff was chosen by an algorithm. And you can see that this is, again, a sparse generalized additive model. This one has integer coefficients, which are here. It's actually a computationally hard problem, combinatorial problem to design these things, because you have to figure out which subset of features work together and how to use them to form a model. Now, anyway, hopefully you can see the value of sparse additive models by this point. The interpretable recidivism paper that I mentioned at the beginning of the talk also used sparse additive models. So now I've shown you sparse additive models for seizure prediction, talked about the ones for recidivism prediction, as well as shown you the additive models that were used for the FICO challenge. And we are still working on this. So what I'm going to do now is tell you about the latest paper that we've written on this topic. And this paper was just accepted a couple weeks ago to AI Stats, and it was written with my forever collaborator, Margot Seltzer, and led by two of our fantastic students, Jiachong Liu and Chudi Zhong. All right, now the problem that we're solving is this one. This is just minimize the logistic loss with L0 regularization, which means try to keep it sparse, try to keep the number of terms in the model very small. L0, by the way, is better than L1 because it doesn't have the bias of L1 that shows up when you want a really sparse model. So this is, again, just the logistic loss, just keep it sparse. And then, of course, the model is linear. And the model translates into a conditional probability using the standard formula for logistic regression. Now, to get a generalized additive model, the simplest way to do that is to transform the variables before you do anything, like just as a pre-processing step. So for instance, if you have age as one of your X variables, then you can transform age into lots of dummy variables. And so now you've got a lot more features because you blew up the feature space, but now you can create very flexible functions of age, since logistic regression will give you like a weighted sum of these like step functions. And the result can be very flexible, right? If you add up a weighted sum of step functions, you can get kind of anything that's like any shape that you really want. And then sometimes just to give us some computational like benefit, we might add in a very small L2 regularization term just to help with convergence. And like the vast majority of machine learning algorithms, to minimize this objective, we are going to use some variation of gradient descent. And in particular, we're using coordinate descent, where you adjust one coefficient at a time. And since we want models that are sparse, we're going to be continually trying to send coefficients to 0. Now, we're also going to try out lots of feature subsets that seem promising according to the objective. Okay, so as I said, we're going to do coordinate descent. So we're going to minimize our objective just along this one coefficient, right? This one coordinate, which is one coefficient at a time. Why do we do that? Again, it's because most of the time we're trying to make decisions about whether to set the coefficient to 0. Now, one way that people usually do minimization of like this function, because you want to go from here to here, but you don't know where this is, right? So one way that people usually do this is they might use an auxiliary function, right? This is all in one dimension. Everything here is in one dimension, right? So you might want to use an auxiliary function. So you start here, you start somewhere, and then to get here, what you do is you create this auxiliary function and you go to the minimum of it, which is here, right? This is all in 1D, so it's quadratic and easy to minimize. Go here. And then you would repeat this. You would create another auxiliary function here, and then go to the minimum of that, and then you keep stepping like that. Now, typically, like I said, you'd repeat this computation, but we found out it was slowing us down to repeat it, and we never got past the optimal value this way. So we decided to use a more aggressive step size, so we would go twice as far. So whatever step we took here, we'd go twice as far. And that step was often on the other side of the minimum. And when it is, we can use cutting planes. So we can create a cutting plane aiming this way to try to bound that minimum there. And we could put another cutting plane over here, but we decided to kind of narrow in a bit first, which is to find the midpoint there and put a cutting plane on that guy. And so now we have two opposite facing cutting planes, so we can create a lower bound. Now, if the cutting plane at this point was facing the other way, then we wouldn't have two opposite facing cutting planes. So what we would do is use these 2 points, which were opposite facing, instead of using these 2 points. Okay, so now I'm going to just zoom in a little bit because I'm like really, my bound is a little bit too tight, which is sort of good for computation, but bad for my explanation. So I'm going to zoom in a little bit there and just I made it a little bit rounder so you could see it better. And now we have our 2 cutting planes, and that gives us a lower bound on the objective. So now, if it happens that earlier in the computation, like maybe way earlier, you had found a solution with a better loss than our lower bound, then adding in this feature j, even if it's at the best possible value, like coefficient value, is only going to make us worse than what we had so far, okay? And so we don't want to add that covariate in. It's only going to hurt us. It's not going to help us, even if we chose its best possible value. And so we just set it to 0, and we go searching for a better feature. So that's how it works. So you rotate through the coefficients using this bound to see whether the coefficient should be 0. And if not, you just choose the minimum over here, okay? Now you can see that we did a lot of work to get very tight, really fast, tight lower bounds here. And it turns out that we can get even tighter lower bounds if we use quadratic cuts instead of cutting planes. And this technique really helps us to prune the search space so that we know when it's not worthwhile to add in a feature. And this is all really fast, by the way. We can do very many iterations very, very quickly and search over the whole space of combinations of coefficients. Now, that's the basic idea of that technique. I mean, obviously, there's a bit more detail that I didn't include, such as, we have a priority queue for which coefficients we're going to check in what order and so on. But we also found what we think is a really helpful way to reformulate the whole problem to make it even faster. So as I showed you, right, we're using the logistic loss, which has its why do we want the logistic loss? And we want it because it has this probabilistic model, right? We can get estimates for conditional probability. Now, as it turns out, we can reformulate the problem by using a different loss function. We can use the exponential loss rather than the logistic loss. And now I know we really want to do logistic regression here, but to be honest, exponential loss does pretty much everything the logistic loss can do. And you still get conditional probabilities, right? The only difference is the equation's a little different. It has these 2's here, right? This is logistic regression. And there's no 2's, and then here's the exponential loss formula with just the 2's. And so you get everything that logistic regression gives you, but you get more, right? There's a major advantage because, as it turns out, if you're using dummy variables in the exponential loss, it turns out you can get an analytical solution for the line search. It's like, some function. It's a complicated function, but you can calculate it. It's like, if this is true, then the value is this. If this is true, then the value is that. So, there's no like cutting planes. You don't need cutting planes. You don't need quadratic cuts. You don't need anything. You just sort of plug the formula in and off you go. And this makes it really fast. Okay, so it does everything that logistic loss does and more. It's just like the magic of the exponential loss. Anyway, now by running this technique, which is like, coordinate descent plus bounds, and optimizing the heck out of each iteration of the code, we can get very, very sparse additive models really, really quickly. So we have this algorithm that produces fast, sparse, generalized additive models. So let's go back to the FICO data set here. We decided to try to construct a sparse, generalized additive model on this data set. So when we took the data and we created dummy variables between every 2 neighboring values in any continuous feature, you get this many binary features, which is like a lot. But almost no matter what regularization parameter you use, the logistic regression algorithm with the quadratic cuts finishes in under a minute, And the exponential loss formula finishes in under 20 seconds. And the accuracy and AUC are excellent, right? They're very comparable to the best test set performance among the black boxes. And on the next slide, I am going to show you one of the models that came out of this algorithm. And I can do that because it fits on a PowerPoint slide. So this is just the whole model right there. And you just get a score for each of these features and you add them up, right? That's the whole calculation. Just looking up the points for each feature and just adding them up. Okay, so let's look at some of the factors here. So months since oldest trade opened. So if your oldest trade is recent, you get more risk points. And if the number of satisfactory trades you've had is less than 10, you get more risk points. And this external risk estimate, it seems to be like a pretty, a pretty good feature. And it's especially sensitive between values between 60 and 80. But what's really shocking about this model, besides its simplicity in describing this difficult benchmark data set, is the fact that we created it in under 4 seconds from a data set with over 1,900 features. And that's how fast this algorithm runs on average. It's usually about 4 seconds. And again, as I told you, the competition, they told everyone to create a black box and explain it. And they told us this because they didn't know it was possible to create a model like this at all. And we did it in under 4 seconds. Like, you just can't get to this level of interpretability if you're taking a black box and trying to explain it, like to figure out which features are important, right? Here I know exactly how important each feature is for every prediction because it's right there on the screen. All right, so now I've covered our latest approach to sparse generalized additive models. And so I want to switch over to talking about decision trees. Now, I showed you the Corals algorithm earlier. Corals produces a one-sided decision tree. And decision tree algorithms have been popular since the very beginning of machine learning, right? The main problem that's always plagued decision tree algorithms is their lack of optimality, because they've historically been greedy myopic algorithms like C4.5 and CART that construct trees from the top downward, and then they greedily prune the back afterward. And the problem is that if a greedy algorithm chooses the wrong split at the top of the tree, there's no way to undo it. So here, if I'm trying to predict whether I'll get stuck in traffic on my way home from work, well, maybe rain wasn't the first question I should ask if I want a small decision tree. But so these greedy algorithms produce suboptimal trees, but it's hard to improve over the greedy methods because decision tree optimization is really hard, right? Both theoretically and practically. There's a huge combinatorial explosion in the number of possible trees that we could consider. And in fact, constructing such trees is NP hard. It's factorial in the number of variables. And so that's why a lot of people still use greedy algorithms. But there's been, and here's the first, by the way, this is the oldest, this is the first decision tree method, since the 1970s, people have been using these greedy algorithms. But there's been like a real renaissance of interest lately on optimal sparse decision trees. And what all of these new approaches are doing is constructing fully optimal trees. So the user picks the objective, like classification accuracy or weighted accuracy or AUC or whatever you want. And then we trade off with sparsity for interpretability, right? We want the tree to be small, just to have a small number of leaves. And so there's been several different types of approaches for doing this, including genetic programming and neural networks, which have no guarantees whatsoever. Like, you have no idea if you've gotten a good tree when you use those methods. Mathematical programming solvers, where you put it into a solver and you tell it, give me a tree. And I'll particularly mention Binoct, which is I think the best one of that class. And then the technique that's been really quite useful is dynamic programming combined with branch and bound. And I've already shown you an algorithm that uses that, which is Corals. I didn't tell you it worked though. I'm going to tell you how the ghost algorithm works. So this is an algorithm that I designed also with Trudy and Margot, but this time also with several additional students, Hayden, Jimmy, Reto, Ilias, Jacques, and Diane, and Tynan. And the idea of Ghost is that it's, like I said, a dynamic programming method with branch and bound. So I'm going to just tell you how that works. So the type of problem that Ghost solves looks like this. You want to minimize misclassification error plus some constant times the number of leaves in the tree. And if like C is a trade-off parameter between the two. And so if you're willing to sacrifice 1% of training accuracy to get one fewer leaf in the tree, then you would set C to 0.01. Okay, so C has itself has like an actual meaning because everything here is discrete. And then when you solve a problem like this to optimality, you get a sparse accurate tree. So here's an example of a result of solving this problem on the Florida rearrest data. Okay, so here, for instance, we would say, oh, does the person have more than 3 prior offenses? If so, predict arrest. Otherwise, you have to ask about their age. If they're above 26 years old, let's predict no arrest. But if they're less than 26, then we ask about their prior offenses and so on. Okay, so the way these algorithms work is that they start with the full data set in one leaf. So here, my whole data set is just in this blue leaf. Everything's predicted as blue. And then I create every single decision tree with one split. Okay, so I create every single decision tree of one split. And I could only fit 3 of them on the slide, but really there would be quite a lot of them. And then you do this recursively. So you create every decision tree, for every split, you create another set of splits, and you just keep going. So this you can understand this. This is huge space of trees that we're sort of enumerating here. And you just keep doing that until some things happen that will, I know it sounds like big and crazy, and it is. But there are some major things that help us out. So for instance, here, I can't split anymore because that's a pure node. So they're all the same class. So I don't want to keep splitting. And then over here, what I notice is that this subtree is the same as that subtree. So if I solve either one of these subproblems, like if I find the optimal subtree for this little chunk of data, then I can pass it back over to this guy. And then he can use it in his optimal tree, okay? So I consolidate all these duplicated subproblems, and that helps me reduce the search space a lot because I end up encountering the same subproblems a lot. Okay, now I've of course run out of space on my slide, so I'm gonna expand it outward this time so I have more space here. So here I go, so off expanding, right? So you just enumerate all those subproblems, and then once you've solved all the subproblems, you know where the optimal solution is because you've enumerated everything, right? And then you just put it all back together and form the optimal tree. And you're saying, well, there's no way you can actually do this in practice, but you don't. I'm hiding something from you, which is that there's a way to prove that some subproblems can yield non-optimal solutions, and that's with a bunch of theorems. And so these theorems they're analytical bounds, and they reduce the size of the search space. And these theorems show that some partial trees can never be extended to form optimal trees. So you take these theorems, and the theorems literally reduce the search space to something that's actually searchable. So I'll show you an example of one of these bounds that's particularly important. This bound is called the hierarchical objective lower bound. So let's say that you're constructing this tree. So you're in one part of the search space and you're constructing some partial tree. And in this part of the search space, you've decided to make these leaves. In another part of the search space, they won't be leaves, they'll be branches. But here in this part of the search space that I'm working in, I've decided that these are going to be leaves, and that I haven't figured out what to do yet over here, but they're not going to be leaves. I'm going to do some splits. So I can take my objective, which is like this, and I can break the loss term into losses for the fixed leaves and losses for the unfixed leaves. And the losses for the fixed leaves are so 23, okay? For the unfixed ones, I don't know what the loss is because I haven't built the tree yet. And so I'm going to lower bound that loss by 0 because it's possible that I could get all the data points right when I extend the tree. And so I'm going to call this my lower bound B. So this bound is my hierarchical objective lower bound. So let's say that I have already found a tree, like my current best tree that I've seen so far. It had only 3 leaves and it missed only 12 data points. Well, hold on, the tree that I'm working on right now, that has at least 23 missed data points, and I have at least 4 leaves. So the tree that I'm building, it's never going to be as good as this tree. Like, this tree is just strictly better. And so because of that, that means that the tree that I've already seen is strictly better than anything I could get on my current, by extending my current tree. And so what that means is that my tree and all of its children can be eliminated from the search space, because this tree and any of its children will never be as good as the current best, no matter how I extend it. Even if I get 0 error and add no more, even if I get 0 error in here and extend it even just at all, I'm not going to get anything as good as what I've already seen. So this is called the hierarchical objective lower bound, and I'll just put it here into a theorem. And it just says, yeah, if the best tree we've seen so far is better than the best we could hope to do on our current partial tree, then we shouldn't work with our partial tree anymore. Now, there are a whole bunch of these bounds that work together with this one to chop off parts of the search space. And each of these is a theorem, so I don't have time to explain them. And I know for you, it just looks like a bunch of words on the page, but for me, it's like a bunch of superheroes, like trying to save the world in different ways. So I think what I'm going to do is I'm going to skip a few slides here and just show you kind of an example of how it performs on the FICO dataset. So this is a tree that we constructed on the FICO dataset. Again, the dataset has 10,000 data points with over 1,900 binary features. We put a depth limit of 5 on the tree. Our training accuracy was 72%. Now remember, the best thing you can get on this dataset is 73%. Our test accuracy was very similar. It generalized nicely. This tree has only 10 leaves, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we constructed it in 8.1 seconds. Okay, so this is, to me, this is, it's got only 10 leaves, which is really remarkable. I mean, you can even look at this tree and see what it says. Like, it says that if the external risk estimate is really low, then I know what to do. Or if it's really high, then I know what to do. I go over here. The decision's clear. Otherwise, we have to start asking some more nuanced questions, like, okay, what's the percent of trades with balance? And what's the average Munchausen file? And so on. Okay, and again, to remind you, this is not an easy data set. This is a benchmark data set, and we didn't know it was possible to construct a single decision tree with this level of accuracy until we did it. And in fact, without the ghost algorithm, I don't really know of another way we could have done this, because I didn't know we could get to this level of sparsity and maintain black box performance. So this is the kind of result that we're aiming for, and I'm sort of, I'm thrilled after all these years that we got there. So now I've covered these 2 topics, and I've showed you the current fastest techniques for these 2 really important problems, and that they can get really remarkable results for challenging benchmark data sets in just seconds. And so what I'm going to do now is go back to talking about real-world concerns in criminal justice. Now, one thing you need to know that I haven't discussed is the fact that people like to explain black boxes, and black boxes, explanations of black boxes are not the same thing as interpretable models. Okay, and in particular, people often like to say that they're explaining a model when they're just approximating a model, and this is very problematic, because if you create a model that approximates a black box, like here, it's approximating this black box in this area, this point, then this is an approximation, right? This is not an explanation, because the explanation and the black box could use totally different features. So for instance, it's possible that you could take a black box for criminal justice and approximate it with a function that uses age, priors, and race, when in fact the black box only depends on age and number of priors, because again, these race is correlated with these things because of systemic racism in society. And then what could happen is that you might not know what's in the black box, so you might look at the approximation and say, oh, this model depends on race, and therefore the black box depends on race. And that would be a naive thing to do. And you could say, well, nobody would make that mistake, right? That's a very silly mistake. Nobody would do that. But the fact is that they might make that mistake. And they actually did make that mistake. And in particular, it happened with Compass. And it was exactly in the ProPublica article that I mentioned in the beginning of the talk, this very famous article that everybody in the fairness community kind of works from. This is exactly the mistake that they made. So they took the Compass scores and they approximated Compass with a linear model, and it depended on race. And then they declared then that Compass must also then depend on race. Now you can't do that. Okay, so to see why this doesn't work, I want to look at the data. So I'm just taking the data from Florida that was used in the ProPublica piece, and we just plotted it. So here I'm showing you a plot of Compass violence score versus age, and each dot is a person in Florida. And so I hope you can see this, but like there's a very sharp cutoff of Compass score as a function of age. So if you're like 20 years old, you're not going to get a Compass score of -4. Like that's just not going to happen, right? You got to be like 50 years old to get that. And I mean, there are a few outliers, right? But overall, like this is like a pretty, you know, it's like a pretty clear function, a function of age. And, you know, we hypothesized that this might be Compass's dependence on age. Like we don't know that, right? But we're hypothesizing that because of this very clear dependence. Like maybe these were just like typos or something. Anyway, this is not pointing to a linear function of age, right? It looks that like, you know, I can't think of what linear function you could put on there that would be a good approximation. But in any case, this is, you know, Compass depends heavily on age over here. Like this is a really heavy dependence on age. So if ProPublica messed up the dependence on age, that could definitely mess up their analysis. So what we decided to do, we still wanted to know, does Compass depends on race? Like what, like does it? And so we subtracted out this function of age. And then we tried to, we tried to figure out whether Compass minus this function of age depends on race. And it didn't seem to. We ran machine learning methods with and without race to see if they need race to predict Compass well, and they performed similarly. Race just doesn't boost performance, okay? It's just like in our interpretable recidivism paper with the additive models. Like, it just doesn't, race is just not, it's just not in there. So ProPublica's conclusion is pretty shaky. And so then if race doesn't actually appear in Compass, other than through its correlation with age and criminal history, then how did they find these pairs of people? Because the white person, right, these are pairs of people where the white person has this like long criminal history and the low Compass score, and where the black person has like this tiny little criminal history and like a really high Compass score. Now, the thing is, if you look at these two people, the black person is much younger than the white person. So if Compass depends heavily on age, that could totally explain how this happened, right? Vernon Prater, he's old, so he doesn't get the age points. And I'm not saying that I agree with this, but if they had compared two people of the same age, it would be much more convincing that Compass depends on race in addition to this like strong dependence on age. So ProPublica's claims like not really holding up with respect to race. Compass might not actually depend on race. But I think there's a much worse problem with Compass that ProPublica completely missed, which is that the lack of transparency with Compass masks a lot of problems with the data. So here are some people who are predicted to have the lowest possible risk for a future violent crime. The scores range from 1 to 10. These people had a score of 1. And look at their criminal histories. I mean, you know, aggravated battery, something bodily harm, aggravated battery with a deadly weapon, robbery with a deadly weapon. Like, these are not people I would expect to get the lowest possible Compass violence score. Like, I don't know what's going on with that. I can't explain this other than a data issue. And this is only the tip of the iceberg. These are people with Compass scores of 2 and 3. And this is the number of arrests and prior charges that they've had. Some of these numbers are huge. Like some of it's like solicit to commit armed robbery and again, kidnapping, attempted murder. Oh my gosh, you know, like how could you get such low scores, right? And we even, there must be typos all over this database. And we even think we found typos in the documentation from the company that made Compass. So they claim that they claim it's a linear function of age. We think it's a nonlinear function of age, like I showed you. Anyway, we published this article attacking both ProPublica for explaining a black box wrong and Compass for being a black box. And we published it in the Harvard Data Science Review. And the editor of that journal, the famous Zheli Meng, he solicited a whole bunch of commentaries from famous criminologists and legal experts. And then one of the commentaries was from the company that makes Compass. And they wrote an absolutely scathing article saying that Compass is interpretable, which is pretty funny because if that were true, it would have saved me and ProPublica a lot of trouble. But in the mountain of criticism there, they admitted a couple things that were super interesting. Like they wrote that the authors, so us, we've taken a clearly informal description of the violence score in the practitioner's guide, and it wasn't intended to be a technical document. Now hold on. That was an equation I showed you from the practitioner's guide. So they say it's informal, but I don't think so. They said discussions of appropriate transformations are beyond its scope, and we note that the skewed age variable is an ideal candidate for a normalizing transformation. So we were like, oh my goodness, it's like they actually admitted that that we were right about the practitioner's guide not representing the true Compass score. And then they also wrote a section on transparency and said that they were trying to pursue copyrights for these scores. And we were like, oh, maybe we actually did something good in the world, right? Who knows? Okay, maybe we'll go back to using interpretable models in criminal justice. All right, so just to summarize, I talked about the Rashem Unset theory, which attempts to explain why there's no trade-off between accuracy and interpretability, which is that there's just a lot of good models, and so hopefully one of those good models is interpretable. And then I talked about the two kind of holy grail problems in interpretable machine learning, in my view, which are sparse generalized additive models and optimal sparse decision trees. And then I want to point out that the combination of the Rashem Unset theory plus these fast algorithms has vast implications for society, because it means that we can insist that models that determine people's freedom in the world of criminal justice be something that people can scrutinize. And it means that healthcare models could be more reliable and easy to use. And it means that loan decisions could be less inscrutable. And this would be a major step forward to being able to get powerful machine learning models actually used in practice for high stakes decisions instead of sitting on a shelf because they're too complicated. All right, thank you very much.
Thank you so much, Cynthia, for the wonderful presentation. So let's give a round of applause. This is wonderful. Thank you. And I already have a lot of questions from the Q&A panel. So because of limited time, so let me just start off with some questions. But if you have additional questions, feel free to ask. Cynthia, I think on one slide you discussed, you could have a general area of good models, and then work on, for example, some constraints in that good models. How do you define good model, especially in the context of your work?
Yeah, so good model means it has loss within epsilon of the minimum. So it just means like the logistic loss is within epsilon of the best you can get for your model class.
I see. The other question we have is when we talk about the logistic, regression analysis. I think there are a lot of interest about this quadratic Cartesian plane approach plus auxiliary function. Can you maybe tell us a little bit whether that's also can be applied to non-smooth convex problems? For example, non-smooth convex aeroplanes. I think that is one question from our audience.
We haven't tried to prove it for anything except logistic regression. Like you have to prove that whatever quadratic cut you create, you have to prove it's a lower bound for the loss. And so it's possible that you could use it for some objective that's not smooth, but you would absolutely need to prove that whatever lower bound you created is actually a lower bound Otherwise, you won't be able to use it. You could accidentally, if these two functions intersect each other, then you won't be able to get a lower bound from it, and you could accidentally cut off the optimal solution. So you actually have to prove that.
I see. Thank you. The other question I think is quite interesting is I think people were very surprised at how fast your algorithm was for the fecal data set. I think the audience is wondering whether there's some expected convergence time, let's say in general for this dynamic programming branch and bound. Let's say you have N features and the D depths. Is there any way that we might be able to get any guarantee on the convergence time?
So the problem is exponential. Factorial. It's factorial in the number of features. It's NP hard. So at some point, the runtime will blow up. If you have too many features, the runtime will blow up. And so the question is sort of, how many features can we get before it blows up? So I'm just gonna share my screen again, because I have a really good answer to that on the screen, and I just ran out of time and I didn't get a chance to talk about it. So I'm just gonna pop it up on here. So this is showing scalability of this algorithm. So so something like CART, which is a greedy method, would take almost no time, right? This is time number versus number of features, right? So CART just takes no time no matter what, because it's just greedy, but it produces non-optimal trees. So you lose a lot of performance when you do something like CART, which is a 1984 algorithm. And then what I'm showing you is a bunch of different methods. So this method over here is DL 8.5, which is it's actually a very good algorithm. It's again it's a dynamic programming with branch and bound method. And you can see it blows up after about 25 features. It just sort of, takes a very long time when you have 25 features. And then this blue one is the Python version of our code. Our code benefits a lot from a lot of, the bit vector libraries and stuff that we're using in C that I didn't have time to describe today. And then this brown method is our method from last year. And then the blue one is the method I explained to you. This is Ghost. Generalized and optimal sparse decision trees. And it blows up, but it takes 100 features to get there. And that's where we want to be, right? We want to finish in under 10 seconds for like over 100 features. And that's where we want to be.
Thank you, Cynthia. That's really helpful. And I think we're sort of run out of time, but let me go with the one last question. So for this Florida recidivism data set, there's a question about whether it is only counting people who have been released, or whether it takes into account, let's say, some sort of counterfactual recidivism of people who have been jailed for a long time but not yet released. Is there any bias, associated with this particular data set?
Yeah, okay. So this data set, the whole story behind this data set is crazy. So first of all, they were using the wrong COMPAS score. So I think they were using like the COMPAS parole score for like bail decisions or something like that. I'm not really sure. Like they were using it to figure out, so it's like, the whole mechanism for this whole situation is sort of really weird and messed up. And every criminal justice data set I've ever worked with is sort of weird and messed up in its own way. But you don't know how long people have been to prison for. Like you don't have that information. You pretty much never get that. But we were told we also did a study in Kentucky, and we had data from Kentucky for like tons and tons of people, thousands, hundreds of thousands of people. And they basically said, we don't know how long people have been in jail, but you should assume that they haven't been there for very long. So you should assume that like of the 2 years or 3 years, however long you're predicting, that they haven't spent most of that time in prison. And we were like, okay, well, that's the best we could do. So yeah, so that's something we've definitely thought about and tried to deal with. But I think for all of these data sets is complicated. I think the thing we'd really love to get, for instance, is like drug use information or like alcoholism. Like that would really tell us a lot about these people and whether they're likely to commit crimes. But I've never seen a good criminal justice data set that actually had proper information on alcoholism.
Thank you. Thank you so much, Cynthia, for the wonderful talk today. I think it's certainly very inspirational about your takes on interpretable models and also your new studies along this line. We want to thank everyone who participated in today's distinguished seminar because we don't have time to go through all of the questions. So please feel free to reach out if you have any additional questions. And meanwhile, I want to thank today's sponsor for this distinguished seminar, the Center for Responsible Machine Learning, Center for Information Technology and Society, and the Mellon Champion Initiative on Mind and Machine Intelligence. And of course, thanks everyone for joining. And Cynthia, we hope to see you on campus for future events. Thank you so much.